Hello everyone, welcome to lecture 8. So in today's lecture, we are going to learn about a few more sorting algorithms, and particularly we will begin with heap sort. So before we can go into heap sort, let's define what is a priority queue. So priority queue is clearly defining a queue which allows you to extract the minimum or the maximum key. So the key operation that we are interested for a priority queue is that we want to identify or remove an entry whose key is the lowest. Or it can be formulated as identify or remove an entry whose key is the highest, but not both highest and lowest at the same time. So this is the key operation we are interested in. And you can think of, just like we had discussed in the binary search tree, the notion of a dictionary. So dictionary is having a key and value pair. So the search typically is done with respect to a key. And then once an entry is found containing the specific key, then all the values that are associated with that entry can be retrieved. So overall, in the priority queue, we are trying to identify or remove an entry whose key is the lowest. And another important aspect that we are interested in is that we would like to be able to insert any key at any time. So we want this flexibility. And even with this flexibility, we want this operation of extracting the lowest or minimum value, minimum key entry at the fastest possible way. So how fast? It can be as close as order of 1 or constant time. So how can we achieve that? So before we get into achieving this goal, let's look at an example of where this could be relevant. So one common application of a priority queue is the event queue management. So in an event queue, you can think of, there are some identifiers to identify the events, and they could be carrying some numbers like 5 colon with particular description E1, then can be 8 colon E2. So in this way, you have stored in a particular data structure, and then you want to insert an event at any time. So you may introduce a new event, let's say 9 colon E3 into this event queue, and then that will automatically account for, so this new entry. So 8 column E2 and then 9 colon E3 after the insertion. And then at this point, if you ask remove min or trying to extract the lowest possible entry, then this should be able to give us 5 colon E1 as our answer. And then after the remove min operation, then the new configuration would look like 8 colon E2, 9 colon E3. And at this point, one may just simply want to not remove min, but just ask for what is the minimum value. And it will give us 8 colon E2. So in other words, we are focused in these two operations, remove min and min, as far as the priority queue is concerned. So now the $1 million question here is how to implement this behavior efficiently. And the answer is binary heap, which is essentially an implementation of a priority queue. All right, so now let's try to understand this data structure. Before understanding how this can achieve the efficient implementation of the min and the remove min operation. So what is a binary heap? So binary heap is fundamentally a complete binary tree. So what does it mean by complete binary tree? It means that every level is full except possibly the bottom level. And that bottom level may not be full, but it is filled up from left to right. Okay. So let's take an example. So you can have 2, 5, 3, 9, 6, 8, 16, 11, 10, 4. So apart from the property of the binary tree, as you can see, it is filled up from left to right. It is complete because all the levels are full except for the leaf level, which is also filled up from left to right. So this is the most essential property of a binary heap that it must be a complete binary tree. But what makes it a binary heap is the heap order property. So the entries in a binary heap satisfy the heap order property. So what is the heap order property? So heap order property states that no child has a key less than its parent's key. So no child has a key less than its parent's key. So let's look at, for example, 5 and 6. So 6 is a child of 5, and we find that it is greater than, that the key is greater than its parent. Take any part of this tree, you find that the parent's key is always less than the keys of the children. So let's see what this leads us towards. So this is oftentimes stored as arrays of entries. By level order traversal. So what do we mean by level order traversal? That means we are going level by level. So if you go level by level, we have 2, then 5, 3, then 9, 6, 10, 4, then 16, 11, 8. So to traverse in this order is the level order traversal. So it is often stored as arrays of entries. So this is the most interesting aspect of a heap, that one can visualize a heap in the form of a tree, but the storage need not have to carry the notion of a tree. And that is possible because of the properties that we discussed, that the binary heap is a complete binary tree. And this allows us to realize the structure in the form of, or represent the structure faithfully in the form of arrays of entries. So let's say we lay down the level order traversal for the above tree. So it's going to be 2, 5, 3, 9, 6, 10, 4, 16, 11, 8. So if the indices are going from 0, 1, 2, 3, 4, 5. So this is our array where we are storing the keys of the binary heap. So how many elements are here? So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So 5, 6, 7, 8, 9, and 10. So what we want to do is that we want to leave this first, the 0th entry empty. And you will see shortly why. So all the valid entries are stored from the index 1 onwards. Okay, so now let's lay them down. So 2, 5, 3. Let's say 2, 5, 3, 9, 6, 10, 4, and then 16, 11, and then 8. So let's place this side by side. Now let's bring our attention to some interesting property on the basis of which we would be able to traverse, just like we would traverse a tree, but just involving the array indices. So these are two equivalent way of looking at the representation, but it is still not obvious how by storing in the array, it can take up the structure of the tree. So what would be the way to convert or map the nodes to the indices? So the property is as follows. So node i's children can be accessed by multiplying I with 2, so 2 times I, and 2 times I plus 1. And node i's parent can be accessed as I divided by 2. So this notation is signifying that we are taking a floor of the value. So in other words, if it is 5 divided by 2, then the answer is 2. So let's see how this property is mapping. So if I just label the indices here, you will be able to see the property coming through. So let's change the color. Okay. So I'm just going to put up the index of each of these entries. So this is 1, then this is 2, 3, 4, 5, 6, 7, 8, 9, 10. So now you can note here carefully that if I take a node, let's say this node containing the key 5, the index of that is 2. So I'm picking on this node. So if I pick on this node and I want to go to its children, what do I apply? 2 times I. So 2 times I is 2 times 2, which is 4, and 2 times I plus 1, which is 5. So the fourth and the fifth entry will be the children for this particular node. Likewise, if I pick this entry and I'm interested in going to the parent node, so we look at the index, which is the index number 6. And so how do we traverse to the parent? You just do I divided by 2. So 6 divided by 2. So it gives us this third entry. So the parent is directly obtainable from here. So 6 divided by 2 that gives this as the parent of this ith entry. So in this way, you can see that just by applying this simple arithmetic over the indices, you are able to traverse through the tree. Okay. So with that understanding, now we will move forward in understanding how the operations may look like. And the key operations that we are interested in, as usual, is in insert. Then in this case, because there is a priority queue representation, so what is the minimum value? Or you can say extract min or remove min operation. So these are some of the important operations that we are interested in. So let's go step by step. So first is, how do we get the min value? So in this case, to get the access to the node is essentially getting the index corresponding to the stored entry, right? So we can say int min, because this is simply going to return the index. So how do we find the min value? So based on the property that we just discussed, that what makes it a heap order property is that no child has a key less than its parent's key. So therefore, the root is definitely containing the minimum possible entry. So if I look for, so if I'm regarding this as array A, then A of 1 is going to give us the minimum value that is stored. I forgot to mention that we are showing the representation starting at the index 1. You can see why, because if you do arithmetic with 0, you will not be able to directly traverse. Now, of course, you can do some special logic by adding 1 and then performing the operation. You can do that, but it is just more natural to think in a 1-based representation. Okay, so extracting min is very straightforward, and that's exactly what we wanted for the priority queue. We wanted to be able to insert. We wanted to be able to insert the nodes at any time and be able to access the minimum value entry as efficiently as possible. And therefore, this you can see very clearly, the efficiency of this will be constant time, because you just simply are extracting the root node. Okay, so in this particular example, you can see A of 1 is 2. Okay, so the next one is how we can have the insertion. So insert of some key and value pair. So what do we need to do? So let n be the new entry, or you can say newly constructed entry with key and value pair. So the first step is that we place n in the bottom level of the tree. What does bottom level correspond to? Remember, we are maintaining the complete binary tree property. So we are simply going to append to the array. So if I have to insert anything, I will be simply appending to this array. And that amounts to in the tree visualization, just putting a node here. So we place n at the bottom level of the tree at the first open slot from the left. Now, another possibility that can exist is that you're done with this level, in which case you might be adding a new level. So that's one possibility, that you are just adding on to a given level, or you start a new level with the leftmost entry. Now, this comment is more for visualization, but as far as the array is concerned, you can see it is just a matter of putting one more element at the end of the array. So this is what we are storing in memory. But what is effectively happening in terms of the visualization of the binary heap tree is that it would appear to be adding a new level to the tree. So therefore, this corresponds to first free location in the array. So now, if I introduce, let's say, one here. So if I put one here, clearly you can see this is going to violate the heap order property, because one is less than the parent, because the parent is supposed to contain lesser value than the children. So therefore, somehow or other, we have to restore the heap order property. So the point is that this may violate the heap order property. So what do? We have to bubble up the tree until the heap order property is satisfied. So let's demonstrate this. Okay. Okay. So let's say we want to add another entry. So we added, let's say, 2 to the tree. So you have to add a 2 to the tree. So clearly it violated here. So we need to bubble this up. So how is this going to bubble up? So first we're going to fix at this level. So it's going to make a swap here. So this will become 2. This will become 6. Then it will violate at this level. So 5 is still greater than 2. So it needs to swap at this level. So this will become 2 and this will become 5. Okay. So now it has come to a state where both are 2. So it's going to be fine. And now you can see the heap order property is respected. So essentially what we are trying to do to restore the heap order property is that you bubble up the entry. So we are bubbling up the entry until the heap order property is satisfied. So how many comparisons are necessary? As you can see, in the worst case, it's going to be equivalent to the number of levels, the maximum number of levels. So overall, the procedure is that, so you repeat compare n's key. So n is the node that we just inserted. So this is our n. So compare n's key with its parent's key. And recall that checking with the parent essentially means you're taking the index of the current variable. So the index of this variable is 11. So how do you go to the parent node? 11 divided by 2. The index divided by 2, which leads to 5. If you were to go to this node's parent, then again you do 5 divided by 2, which is 2. So in this way, traversal of the parent is all in terms of the index arithmetic. So compare n's key with its parent's key. If n's key is less, if n's key is less, then exchange. And that's what we demonstrated here. And we are going to go on till the heap order property is satisfied. Okay. Next operation is remove min. So here, the minimum value was returned, and that's about it. There was no change in the tree. But in the case of remove min, we want to be able to get the value. So here I'm using integer with the assumption that the value that is stored is an integer. So get min can either directly give you the value of the key, or it may return the index, which can be used to fetch the key as well as the values. It depends on how exactly you are implementing. Regardless, so it's going to return some value, either the index or the minimum value itself. So remove min is not only going to get the minimum value, but also remove the entry from the root. So first step is that remove the entry at the root. And root, we know that is the first element in the array. First, in the sense, by the one based index first. And save the value for return. So you're essentially doing t equal to a of 1 for returning. So this is the step. And then, having removed the entry, what has happened? Let's try to demonstrate. So All right. So removal would essentially mean you literally take this a of 1, which is it's a t equal to 2, and you removed it, which means that now there is a hole that is created here. So what do? You fill the hole with the last entry in the tree. Remember, we are needing to maintain the complete binary tree property. So therefore, naturally, the choice that it has is pretty much left with the last one. So essentially, this is the entry that goes on and replaces this entry. So this becomes now 8, and this is removed. So after doing this, now what happened at this point? So let's see it in terms of the tree. So after 2 has been removed and set aside for returning, we have replaced this value 2 with 8, and this is no longer there. So now you see at this point, the heap order property is again violated. So you can see that 8 is greater than 5, 8 is greater than 3, which is clearly violating the heap order property. So therefore, we need to now restore. So let's say n be the node which moved up the tree. So now this time, so suppose this is our n. So now we have to settle this down at its proper place. So instead of bubble up now, it is bubble down. You have to bubble down n so that heap order property is restored. So what would that essentially mean? So repeat. So if x is, if n is greater than, so here n we are treating as the key for n. So if n is greater than 1 or both of its children, swap n with the minimum child. Okay, so let's see how we are going to execute this. So all right, so let's remove this guy. So we are in a status where we have replaced the first entry already, so which is 8, and this is violating the heap order property. So we have to pick the minimum So which is the minimum value between 3 and 5? It is the 3. So it needs to swap with 3. So it swaps. So after swapping, so this is swap 8 and 3. So we get 3 here, 8 here. Okay. So at this point, as far as this section is concerned, the heap order property is respected. So now our attention goes to where 8 went, which is this region. And you can see that the heap order property is still violated because 4 is less than 8. So therefore, so it's going to pick the minimum of the two, so which is 4. So it's going to swap 8 and 4. And then the configuration would be so you have 3 here. So now 8 and 4 would be swapped. So this will become 4, this will become 8, and this remains as 10. So you can see here, so when you changed something at the root level, then we had to do bubble down operation. When you change something at the leaf level, then we had to do the bubble up operation. So it's either bubble down or bubble up, ultimately trying to maintain the heap order property. And the index arithmetic is allowing you to easily traverse through the tree and perform the intended operation. So one important property to just note here, so every subtree of a binary heap is a binary heap. So in other words, the min heap. So this kind of heap is called min heap. So min heap is where minimum key is at the root. And you can think of the likewise, a heap can also be a max heap, in which case the max key is at the root. So remember, we made a comment in the case of binary search tree, we were able to extract both minimum and maximum value, provided it's a balanced tree. We are able to extract at the log n complexity. But when it comes to heaps, you are able to extract the min at the, so I'm talking about extract min, not delete min. The extract min is possible, just extract in the sense, just fetch the min value. It is possible to do with the constant time, but you are only allowed to get either the min or the max, depending on whether the heap is a min heap or a max heap, respectively. Okay. So now let's look at the complexity here. So you can see that the typical most complex operations so far involved either the bubble down or bubble up operation. And that's also happening along the path. And therefore, anything along the path in a complete binary tree is naturally going to be log of n. So all of this has the worst case complexity of log of n. And so remove min is log of n. Insert is also log of n. But this is order of 1 because you're just fetching the root node. Okay, so if n is the number of entries in the heap, and we know that the heap is a complete binary tree, and therefore this has the order of log n worst case time complexity whenever bubble up or down operations are involved. So that would be a generalized statement. All right. So now let's look at how would we do the overall construction. So this is the bottom up heap construction. So the heap construction would be, so remember one of the properties that we are interested in is that the entries, we want it to be very flexible. So entries can come at any time, and we should be able to quickly maintain the heap order property. So given a set of entries, the goal is to make a heap out of them. So this is our goal. So this is our bottom up heap operation. So first thing is that we do is that we insert the entries or insert the inputs. So entries one by one. So if you insert the entries one by one, so if you have got n entries, so in the worst case, it would be n log n. Because every time you are introducing an entry, it may involve, because you're introducing the entry at the end, so that may involve the bubble up operation, which is log n, and you are entering n times, therefore n log n. So question is that can we do better than introducing one by one and maintaining the heap order property one by one? So heap order property at maintained at every step. So instead, an alternative approach would be, so this is our alternative approach, would be something like this, that you make a complete tree out of the, so complete binary tree. So complete binary tree out of the entries. It's basically in any order. In other words, this making a complete binary tree is amounting to starting at the index 1, just storing in the array these entries. So if you have n entries, 1 to n, you just fill up. So that is your complete binary tree out of the entries. So in any order. So clearly, this is going to create a broken heap for us. So broken heap in the sense that where the heap order property is violated, um, left, right, and center. So what do we want to do? So now we want to walk backward. So walk backward in the sense starting from this entry onwards, starting from here. So we are walking backward. And in terms of the tree, that would mean essentially walking backward. So walk backward through the array from the last internal node. So last internal node means not a leaf. So what would be a last internal node here? Let's see. What is a last internal node here? So the last internal node would be here. This is the last internal node because 4, 10, 16, 11, 8, these are all leaves. So this is the last internal node. So walk backward through the array from the last internal node. So we are going essentially starting from this node onwards, backward. And if you want to see it in the form of the array, so let's see that also. So just for clarity, it's 8 here. Okay, so the last internal node is here. So this is our last internal node in this representation. So this had, of course, this has 2 if you want to be faithful with respect to this representation. So you have 10. So how do we get from to the last internal node? You see at the index of the last node and you divide by 2, that gives us this entry. So that's how you get to the last internal node. So you walk backward through the array from the last internal node. So we are walking backward in this representation from here. Okay. So we are back. So we are walking backward to the root, and which is essentially reverse order in the array. So what is the step that we do now? So after we walk backward, what do we do? When we visit a node, bubble it down. as in remove min. So from here, you take the 6 and we try to position this 6 in its appropriate place by bubbling it down. So at any given level, we keep bubbling down. So let's take an example. Suppose I have just randomly created this tree. So 2, 8, 2, 6. Okay. So what is the last internal node here? So you can see 1, 2, 3, 4, 5, 6, 7. So 7 divided by 2. So this is our last internal node. So with respect to this, we want to bubble down. So bubble down operation, if you recall, we look at the children. What is the minimum of the two values? We see 2. So this is a candidate for swapping. So 7 is what is going to bubble down. So let's just copy this. So after swapping, this becomes 2, this becomes 7. Let's use this. Okay. So we are going backward. So from here, the next candidate to be picked from here, we are going backward from this last internal node. So next candidate is this one. So here the candidate was this. So now we would like to bubble down 4. So again, we see that 2 is less than 4. So you take the minimum of the two children, which is 2. And then this is the swapping candidate. So let's just swap. Move this. So here we are swapping these two values. So now we had 2 and 7 here. Now this becomes 2 and 4 here after swapping. So you can see that we are going backward also in terms of the indices. So 3, 2, and the next candidate would be this one. The next candidate will be this one, going backward. And you can see that it has to pick now minimum of the two children and need to swap. So after swapping, so it needs to swap with either of these two. So let's say it picks this one to swap. So after swapping, so here we had 4, here we had 7, here we had 2. So after swapping, this becomes 9 and this becomes 2. So remember, bubble down operation means it has to repeat. So again, so 9 has come. 9 has come here. So next, the candidate is between these two children, whichever is the smallest. So 4 is the smallest between 4 and 8. So this is the swapping candidate. So let me. Okay. So now after selecting this, just see. Okay, so now after swapping, let's see how the configuration looks. So this now becomes 4 and this becomes 9. And you can see now at this point, we have the full heap property satisfied. And this is our final configuration of the min heap. Okay. So let me pause the recording because we have discussed how to construct a binary heap. And we also discussed how a heap is able to maintain a heap order property, which allows for a very efficient extraction of the minimum value. And we will see how that helps in the sorting algorithm that involves a binary heap.